class? All right, so what I'll do today is I will talk about the solution of the homework assignment that's due today during the lab time, okay? So, but what I'll do now is to give you a new homework assignment. This one is, it's tedious, but it's not hard. Okay, it's a hardware multiplier. I want you guys to build using LogicSim to build a hardware multiplier. It will multiply two 4-bit numbers and get an 8-bit result. Okay? Are we doing okay so far with the overall idea? I know there is a hardware multiplier in LogicSim. You cannot use that one. So what you can use is listed here. So these are the ingredients. You can use two 4-bit input pins. I think that part is fairly easy to understand. Any number of splitters, wires, and junctions. A junction is basically a dot. It connects one wire to another wire. Okay. So any interconnection, using wires and splitters and whatnot, it's okay. Okay. You can use basically a limited number of those things. You have one single 8-bit output pin, okay? You have 3 adders of any width. In other words, you will have to choose the width. If I give you the limitations, you're like, okay, you have to use a width of this, this, and this. That actually helps you to design it. That's why I'm not giving you that. Okay? To make you think about it, okay? Because otherwise, it makes the assignment a little bit too easy, and you're not going to learn how to, design stuff like that. I'll put it in another way. When you start to work for Intel and you're designing processor chip, do you think your supervisor will give you all of the clues, all of the hints of how to do something?
Yes.
No.
Yes.
Well, that would not be the Intel that I know of. That would be probably Wintel, another company. So any number of constants, okay? Constants are, well, technically speaking, you only need one, okay? Because we can use splitters and stuff like that. But it's convenient to have constants kind of sprinkled around the design. So I'll just let you guys use any number of constants just because it is convenient to do so. You can also use any number of AND 2 gates, okay? But only AND 2, okay? Not AND 3, AND 4, AND 2, okay? Now, for those of you who really hate to do things repetitively, copy and paste and stuff like that, you can come up with a subcomponent design following these rules, okay? So if you have your own subcomponent, making use only of these components, you can make as many copies as you need using your own components, okay? So that's not required, okay? I do not require the use of any subcomponent, but if you think it might help make your design, a little bit neater, cleaner looking and stuff like that, go ahead. That is not a problem. Do we have any questions? That's it. I mean, the file name has to be molt.circ, has to be a LogicSim file, and those are the only restrictions of this particular homework assignment. Yep.
Is N2 gate is the N2
2 input and yep.
Okay.
Go ahead.
Are we allowed to use OR gates?
You will not need to use OR gates. If you're thinking about using OR gates, you're already maybe on the wrong track. Okay. Yep.
When is this due?
This is due in a week, so you have 1 week to work on it. I suggest that we get started on this one as early as possible. Okay. All right. But Tack, you never talked about multiplication in class. Well, let's talk about multiplication then, right? All right, multiplication. We'll start with something that you already know, or you should know, or I think you should know, okay? Just because I think you should know doesn't mean other people think you should know, but I'll just go ahead and check. Do we know how to do multiplication in base 10? Okay, I see a lot of nods, okay, but I can see a few faces displaying uncertainty. Okay, so we'll go ahead and have an overview of multiplication in base 10, okay? So I'll pick some random numbers here. 781 times 143, okay? Completely random numbers. So I was told to do the most significant digit first, but some people do it with the least significant digit. It doesn't make any difference, okay? The principle is the same. Okay, so I'll try to do it the normal, usual way. 3 times 1 is, okay, before we do this the long way, let's go ahead and look at the multiplication and figure out what does it mean, okay? What is 143? 143 is 140 and 3. Okay? So when you use the distributive law of multiplication, what do you get? You get 781 times 100 plus 40 plus 3, right?
Yes.
And that obviously is 781 times 100 plus 781 times 40 plus 781 times 3. Is that making any sense? Okay. Now I can say, oh, this is the same as 781 times 1 times 100 plus 781 times 4 times 10 plus 781 times 1 times 1. So technically speaking, I have to do it like a times 3 times 1, sorry. Okay, but why am I doing this? This is the number of places that you have to shift before you add it to the next component, and this is the number of digits you have to shift. The least significant digit does not need to shift because it is already the least significant digit. Are we doing okay so far with the kind of horizontal long way of looking at multiplication? So the way we usually do it vertically is to carry out the multiplication. 3 times 1 is 3, 3 times 8 is 24, 3 times 7 is 21, so this will add up to 23,043. Okay, then we move on to the next one, right? 4 times 1 is 4. We shift it by 1 digit because this is the 40 of the second number, so we shift it by 1 digit. 4 times 1 is 4, 4 times 8 is 32, 4 times 7 is 28, 28 plus 3 is 31. Are we doing okay so far? Okay. So we usually want to do addition only with 2 numbers at a time, because it's just easier to track stuff that way. So we'll do it this way. And you have to do it this way anyway, because the adder that you can use in LogicSim can only take on 2 numbers. You can only add 2 numbers at a time, so you will still have to do it this way. So 3 goes here, 4 times 4, 3 plus 0. Now you have to remember, there's an implicit 0 here. Even though most of the time we do not write it, it has to be here in order for the addition to work. 4 plus 4 is 8, 3 plus 2 is 5, 3, and the 3 here. And then what we do is we look at the most significant digit in this case. 1 times 1 is 1. I mean, shift by 2 zeros first because we're dealing with the 100. So now we have 781 over here. And then we do the addition. So we have an 8, 3, 6, 1 with a carry of 1. So this would be 20. Oops. It would be 3 plus 2 plus 1 is 6. So I got 61683.
No,
That's a 7.
it's a 7, not 2.
Oh, that's a 7. Okay. Bad penmanship, huh? Okay, so that would be 1, 1. So 11683 is my answer. Okay. Do we need another example of multiplication in base 10? Yes? No? Please no. Right? Okay, so now we move on to base 2. Okay, so I'll give you a base 2 number, and I'll write it this way first. Okay, so we'll go ahead and multiply. Let's say 1101. Well, that's not a good number because well, that's not bad. That's okay. Times, let's say 1001. Okay, that's my multiplication in base 2. So if I use a little subscript of 2, this makes it very clear we're dealing with base 2 numbers. Okay, so the first thing we do is the same way we break the numbers down. So we have 1101 times, okay, and we separate the individual digits. So we have 1000 in base 2 plus 000 in base 2 plus 00 in base 2 plus 1 in base 2. Making any sense? Okay. And when you look at 1101 times 1000, the result actually, interestingly, does not depend on the base at all, because the multiplier is a 1 with 3 shifts, 3 digits of shifting. Okay, so this is actually the same regardless of the base. This becomes 1101 with 3 zeros. What about the next one?
Same thing with 2 zeros.
It's all zeros. No, because it is 1101 times 000. So it becomes all zeros. Okay? But I'm going to be a little bit careful here, and I'll just write it down as 6 zeros. The reason why I write it down as 60 is because this 0 here is the actual multiplier. These 2 controls how many digits I have to shift. So that means I only have to shift by 2 digits when I multiply this 0 to this number. Is that okay? Now, I'm doing this the really longhand way for a reason, okay? Every single bit of this stuff is actually relevant to your design. Okay? The next one sounds easy. Anything times 0 is 0. I could have just written a single 0 in base 2 here, but I'm not going to do that. Instead, I'll say it's 0, 0, 0, 0 because of this quantity times that number. But then there will be one more 0 because I have to shift by 1 digit in this case. Okay. The last one is a single 1 times 1101. 1101 in base 2. There you go. So everything is still in base 2 at this point. So at this point, I'm not going to carry out the actual base 2 addition because you already know base 2 addition. Then you can use the adder component inside logic sim, so there's no need to go any further than this. Are we doing okay so far with this? So if I write this out in a vertical format, which is actually helpful because most of you will want to make the design in a vertical format instead of a horizontal format, okay? So it becomes what? 1101 times 1001 in base 2. So, but once you look at it in the vertical format, you can see how easy it is. In base 10, okay, I have to keep track of, 4 times 1 is 4, 4 times 8 is 32, which is 2 with a carry of 2, and then 4 times 7 is 28. 28 plus the carry of 3 from the previous digit is 31. Okay, so I have to keep track of certain numbers, mentally as I perform, 4 times 781. Do I have to ever do that with binary numbers?
No.
No, because the multiplier is either a 0 or 1. In both cases, it is trivial. Okay, but in this case, I have to add 3 zeros to this side, and then the next number is going to be 1, 2, 3, 4, 5, 6. I know it is just a 0, but I'm going to write this out because your design will need this step. Okay, we add these 2 numbers. Okay. Nothing major here. And then we have another 0, but this time we have 5 zeros here. And then we still end up with the same number as before, right? This time we have the 1101, so we have this number here. We add these 2, we have 1, 0, 1, that's a 0, that's a 1, 1, 1. That's my final result. The tag you said 8 digits. So where's the 8th digit? The 8th digit is the carry from this side here. So this has to be in the output pin, even though it's not a part of the actual output of the last adder. The carry of the last adder should be represented in the output pin. Okay? So now my question to you is, how do I come up with these digits over here? These 3 are constant, okay? That's easy. But what about these guys? Or even these guys, okay? So you have to look at the bin of ingredients that you can use, and then you go, okay, so which one should I use to represent a bit here? Which one should I use to represent a bit here? We already know the addition is the easy one, okay? Remember since the projector is on, I said 3 adders of any width. 1, 2, 3. output pin, input pin, input pin. Okay? So the only mystery component is the AND 2 gate. Okay? Constant, 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 constant. Well, no, I take it back. Constant, constant, constant. Okay, let me just use the yellow here. See, I'm doing your homework assignment.
Thank you.
1, 2, 3. Those are constants. Constants.
Yeah, I can't see that.
Well, that's the whole idea. Is that you have to actually watch me while I'm doing it. Or you can also put on a blue filter that will make the yellow really stand out.
Really? Okay. Nope, not working.
Fine, green. Constants.
Nice.
Constants. Constant. Okay. You can figure this out. I mean. All right. So this is as far as I can go to give you that information. The rest you will have to figure out. Are there any questions about this whole thing? No? Okay. You really have to kind of think about it. And as you work on it, okay, because I worked on this myself and go like, wow, the first time I worked on this, it was really tedious. I made things unnecessarily complex, okay? So I ended up with a design that actually works, but it has far more wires than it needs to, okay? So when you work on this, you probably will encounter the same situation where you go like, wow, I got all of these wires flying around, but so the idea is, the trick is you only split when you need to, and you only split into individual wires when you need to. Okay, so don't look at oh, I got 4 bits here, I got to split it into 4 different wires. It is not always necessary to do that. Okay, and you will have to use splitters and mergers, or basically they're the same thing. They work the same way. Kind of throughout the design, because the adders can only take on merged wires as a bus. Okay, like 6-bit, 7-bit, and whatnot. But on the other hand, the AND 2 gates have to take on individual bits. So there are times where you actually have to split it up, and there are times where you have to merge them together. Okay, and you will find some regularity, like some pattern that will repeat in the design. So you might want to go like, oh, okay, since I can see this is repetitive, I'll make a component out of it. So this way I don't have to repeat the same design all over the place. But that's entirely up to you, okay? How you want to clean up and make your design, as easy to maintain as possible. That part is entirely up to you. All right. So are there any questions about the new homework assignment? Yep.
Is it safe to assume that there can be multiple ways to achieve our goal?
The basic idea, there's only one, okay? But how you arrange the splitters and the mergers and the ordering or the adding, that there are many ways to do it. Yep. That's why for certain components I specify as many as you think you need, because different designs will call for different numbers. Because the constants also can come with different widths. Okay, so someone who use a n bit width constant will only require one constant. But if you use individual bits, then you will need multiple constants. So the number of constants and the number of splitters, wires, and junctions is entirely up to you, because it's very individual. Okay. That's also how I can tell 2 people working on it together. It's like, wow, that looks pretty much the same. Okay. Are there any questions? Are there any questions of how far you guys can work together on homework assignments? No questions? Really? Okay.
All right.
Because the idea is you have to, all homework assignments are supposed to be independent and original. Okay? Which means you cannot show each other part of your homework assignment, as a design. Okay, you can share ideas. Okay, so let's say one person know how to do it, the other person does not. Okay, you can use examples like this. Okay, and go like, Okay, so we can see that in this case, these numbers are arranged this way. So you can give the other person a different example, like 0, 1, 1, 1 as the other number, because that would show a different table of all of these bits. So the question is, how do we come up with this bit here? How do we know this is a 1 in this case, but it's a 0 in the other case, and so on? Okay, what component in this list can possibly do that? Okay. So that is something that you guys have to keep in mind, is don't share the solution itself. Okay, you can talk about concepts all you want. Okay, that's fine, not a problem. You can use examples to help each other out. Okay, let's work out this example and see if we can learn about how to do it from the example. That's fine too. Okay, but don't share the actual design or the component in the homework assignment. Like, oh, I think this can be done this way. That would kind of be a really, really gray area already. It's leaning really close to the fence. Okay. Any questions? No questions? All right. So this is your homework assignment. I don't think it's really hard. It's just the fact that I restricted to certain types of components really, really helps. Okay. All right, so with this out of the way, today's topic will be the register bank. Okay, so if you look at the control unit, the overall control unit, some of you might have downloaded my design already. Okay, and you can look at that one if you want to. So the idea is we have a concept called a register bank. A register bank is basically a collection of registers, but collectively it has to do something. Okay, we have to be able to specify, I want this register and that register as the output of the register bank, or I want to specify this register as the input if I want to store a result back into that register. Okay, so it's kind of like looking at this class here as one big register bank. Okay, but the interface into this classroom is not every single person has can access the outside world. Okay, there will be like 2 windows into this classroom to present results from the registers, and there'll be 1 inbox to specify input into the register bank. So the input obviously will consist of the data, but also a specification of which register is going to store this result. The output will be the opposite. We have 2 windows to specify the actual values, but also we'll have 2 additional input windows to specify, I want this register to present the first output, I want that register to present the second output. So that's the idea of the register bank, what kind of interface we're dealing with. So is that concept okay so far as what a register bank is supposed to do? Okay. Can you remind me again, why do we need registers?
Save time.
To save time, okay? Save time from what?
Having to go over to the library.
Going to the library, exactly. So what do we use all that stuff for? When you go to the library, you're getting something from the library or you're storing something into the library. But what are those things? How do we get those items, the data that what is the nature of that data?
Instructions.
Some of those are instructions, very good, okay. But the majority is going to be what? Remember what we talked about last time? The funnel thing that I drew really badly? What was that?
ALU.
It's an ALU, and what is the purpose of an ALU?
Arithmetic logic unit that it does calculations.
It does all kinds of calculations, addition, subtraction, multiplication, bit shifting, and stuff like that, okay? So we have calculations. And do you remember how many inputs do we have into the ALU?
2.
Generally speaking, there are 2, okay? So that's why the register bank has 2 outputs and 1 input.
Wasn't it 3? Wasn't it addition, subtraction, and then bit shifting?
Those are the individual operations inside the ALU. But the input or the number of parameters into the ALU would only have 2 data as input. Because when you add, you're adding 2 numbers. When you multiply, you're multiplying 2 numbers, and so on. Okay? Yep.
So does register have multiple slots to store one at a time, and it puts out 2 of the random slots, whatever you ask for, at once, right?
Well, that's the whole idea of the register bank is it can interface directly with the ALU.
Okay.
So that we can say, oh, we want this register to provide the first input into the ALU. I want that register to present the second input into the ALU, and the output of the register, I want to put it back into this register.
But input is only one at a time, though. It has to like store individually each register.
That's correct. Well, sort of. So we'll take a look at the design, in today's lecture. Yep.
Roll sheet.
Roll sheet. Thank you. There we go. All right. So let's go ahead and take a look at the design. Like, how do we put something like that together? The divide is for my cisp310 class, but I think we can do division too. Bitwise division. Maybe that will make it the next homework assignment. Trust me, it is a lot easier than you think it is, okay? Because if you think about base 10 division, it's really quite difficult. You need to have memorized the multiplication table and stuff like that. And estimate, okay? You have to look at the number, kind of estimate. Well, are there 7 or 8 of these things in this number? Okay, sometimes it's obvious, other times it's not. With binary numbers, it is easy. It really is very easy. All right, so we'll take a look at LogicSim. So Java dash jar LogicSim, and I'll go ahead and create a register bank. This may not be the same as the one in the processor design itself, but it will be pretty close. So in this case, let's go to memory, pick our register, and we'll have a register bank of, let's say, 8 registers. Okay, so we'll make copies of the registers. Okay, 2. Now we have 4. The processor design has only 4 registers. So right here, we already know that this is different. Oh, that is not good. Okay. Shift click is the same. Like most drawing programs, it will allow you to select multiple items. It's kind of like a multi-selected. Get rid of this wire. Go. All right. So now we have 8 registers. Okay. So this is the bulk of the register bank. Okay. But the problem with 8 registers, we only need 2 as outputs at the most, and we only need 1 at the most as the input. So what kind of device do you think we need in order to implement a register bank? It relates to something that we talked about last time.
You said we need how many inputs, how many outputs?
Okay, we got inside a major train station. Okay, we have 8 individual trains. Okay, there are only 2 outgoing tracks and only 1 incoming track. So the question is, what do we need in order to say, oh, this train goes to that track, outgoing track, this train goes to that outgoing track. The rest of the trains stay put.
Demultiplexer.
Multiplexer and demultiplexer. We actually need both because the input is the opposite. Okay. All right. So now that we know that, we'll put the components onto the design first, and then we'll figure out, okay, how do we make connections between these components? Okay. So multiplexer has multiple input and 1 single output. So that's definitely for dealing with the output. So we'll need 2 of these, but I'm going to slap 1 in here first, and then we'll go ahead and change the number of data bits, because the number of data bits of your multiplexer has to match the number of bits of your individual registers. They have to be the same. Okay? It's kind of like, the width of the track has to be the same, throughout the entire station, right? Because, otherwise your train is not going to be able to get out because, it's not the same width. Okay, so that's the first thing we change. What about the number of selection bits? Now that we have 8 registers, how many selection bits do we need? 3, because 2 to the power 3 is 8. Okay, so if you give me 3 bits, I can use those 3 bits to select 1 of the 8 of the registers. So 3 bits here. So that will automatically change your design or the multiplexer to have 8 inputs instead of 2, okay? Which is what we want. So now it's a good time to duplicate the design or duplicate the component so that we now can specify two outputs. Are there any questions about the multiplexers, the role of the multiplexers, why they are here? Okay. If there are no questions, then we'll move on and kind of make the connections. You know, it's really just kind of messy and lots of connections, but for the most part, the idea is pretty simple when it comes to this part. Okay, I'm just going to move this a little bit to the right-hand side, just so that I have room for the input. Okay, and then we'll move these two just a little bit over there, and approximately centered. Okay, it's close enough. Okay, all right. So the first output can be selecting from any one of the 8 registers. So that means, you know, the same register has to feed into both of these multiplexers. Same thing applies to the second register. It also has to go into the same input of both multiplexers. Third one, same thing. Okay, so you can see this part is kind of, oops, I just made a mistake. Here we go. And we also have to remember to go back up here. Fourth one. I see a problem with the fifth one, because now I cannot. Okay, fine. We'll do it some other way. I told you guys I'm not artistic. I think that makes it easier, especially for someone who's not artistic. I can actually do this type of work really well because I design circuit boards. It's just that okay, the first register goes to the first one. So second goes to the second. The rest of this is kind of boring. So, are there any questions when I'm doing something that is kind of boring? Yep.
Can we use multiplexers in our next assignment?
Say again?
Can we use multiplexers in our next assignment?
No. But interestingly, you know, you can implement a multiplexer using a lot of AND gates. A multiplexer would not really help in your next assignment. Okay, so now we have, you know, everything connected to the two multiplexers as outputs out of the register bank. We have one input that will go into the register bank. So let's go ahead and pick out a demultiplexer, and this time we'll make it face north. Change the number of select bits to 3 again, data bits to 8. So now it matches the width of all the registers. So this one has to go, whoops, no, that's not what I want to do. I'm going to move the design all the way up here. So basically, I'm specifying the input of this multiplexer will go into every single register in the register bank. All right, almost there, almost. Okay, cool. We have most of the major components here already. But we still have a lot of wires that are unconnected, okay? We'll deal with the easy ones first, and then we'll deal with the ones that are kind of like, yeah, what do we do with those wires, right? Okay, so the easy ones will be an input pin to the input, okay? That's an easy one. So we just pick one single input pin specify the input data bits to 8, right? And, oh, I just made a mistake, didn't I? Well, there are several ways to do this part. Using a multiplexer is one way. Okay. Let's do it this way. Okay, we'll have one single input pin connected to the data port of every single one. Okay. So now, how do I select which one I want to deal with? I did not leave enough space between the registers. Because these pins need to be connected, and some of these do not want to connect to the same place. So now we have a little bit of a problem.
You can track this.
Huh?
You can connect through the design.
Yeah, I can, I suppose. It's going to be a little bit ugly, but it's okay. So what we'll do is we'll connect the reset pin or the clear pin to one single reset line. Okay, so that's an easy one. So what this is really doing is when your computer starts up, or whenever somebody hits a reset button on a particular computer, the reset line is going to be asserted, and all the registers will be cleared to all zeros. Okay, because you don't want your computer to start off with an unknown state. So as much as possible, you want everything to start with a particular known state, and that's what the reset line, or what I'm connecting right here, is for. So all of these will connect to one single line, and we'll call this input pin a reset pin. Okay, so attach a little reset pin here, and label this pin to be the usual, we call it the reset pin. They use the word clear in Logisim, but it's the same thing as what most people would refer to as a reset pin. Okay. And then the enable is the interesting one, because now that I have all of the data port or the D port of all the registers going to the same input pin, I don't want every single one to update all at the same time. I only want one to update at a time. So that means I need to use the enable, okay, to specify, okay, who am I talking to this time? Okay, who's supposed to be updating this time? So that's what we need to do is with that one. Okay. So we want to use a construct to go from 3 bits into 8 individual wires, and only up to one of the 8 individual wires can be asserted at any particular time. So when you look at the plexers, which one do you think will do this trick? We'll have 3 bits to select, and then up to 8 outputs. It's close to a demultiplexer, but it's not a demultiplexer because it has no input, quote unquote, input into it.
Decoder.
A decoder, exactly. Okay, so we'll use a decoder to get this done. So we pick out a decoder, slap it here. But remember, we have 8 registers, so we have 3 bits for selection. And I will also have to specify the disabled output to be a 0. Include enabled, yes. 3 state, no. Okay, so that's all we need. And I'm gonna move this one so it aligns a little bit better with our registers. Here we go. Okay. We'll hook up. I think I have enough space to do it. It's just gonna be no, that won't be. That's not gonna work. Because I got 8 of these things. Push it a little bit more.
Is there an option just to stretch out lengthwise the decoder?
The decoder?
Just lengthwise?
I think I got enough space now, so I'm gonna start with the last one. Okay, so these wires go to the enable. So what I'm doing here is I'm making sure that I can individually, quote unquote, address each register. So basically I can say, hey, only you should pay attention. I'm only going to let you update your internal state. That's what this is for. And you can also see, when I just draw this by using Logisim, what seems to be the most precious resource when I'm doing this?
Space.
Space, but what kind of space are we running out of? I'm running out of space. Are we running out of space to specify components or
Real estate.
real estate? But what am I currently doing?
Wiring.
Wiring or routing. Okay, this is called routing resources, and that's why when you have a 32-bit or 32 register bank, you're running a lot of routing resources because you can see this is only 8 registers, right? With 32 registers, you have a lot more wires. Now, if you think about each quote-unquote wire, if you have 32-bit registers, each wire going into the D and the Q ports, those are all basically 32 individual wires inside the bundle, inside the bus. So you can easily see, this is routing resource intensive. When you do board design, that's basically one major consideration is that. Okay, all right. But each register is not going to update until the clock pin has a rising edge on 0 to 1 transition. So we're going to bring all of these out. But because of the decoder, now I can have one single clock line going into this design because they can actually share the clock line. So I know this looks really bad because you can't really see whether it's connecting to the clock pin or the reset pin. So that's my fault. I did not leave enough space. But I did not feel like deleting the whole design just so that I have enough pins. So there we go. All right. So yep, go ahead.
So if we were to go and create a component with this and adjust the appearance to minimize the routing resources, we can do that, right?
Yeah, you can do that, but that's only reducing the amount of routing resources from the display or your preview perspective.
Right.
When you put this onto silicon, it will still be the same design and with lots and lots of routing resources chewed up. Okay, so this is almost done. Okay, all of these pins go to one single clock, and we'll just go ahead and specify that clock here. The clock is going to be an input pin. And most processors have one single universal clock for everything, okay? For all the registers, for the ALU, for the memory, and stuff like that. Okay. And now we have these pins that we have to also connect to. So one is enable, okay? The other one is the selection pin. We're gonna do the same thing, okay? So all of these will be individual pins or input pins. And we'll make these face north, because I don't have space on the other side anymore. Go ahead and specify these 2 pins. One to go here, and then this one is going to have a little bit of a problem because I cannot do a single one like that. So we'll have to modify this to a 3 data pin one because it's selecting one of the 8 registers. Okay, and we'll label these accordingly. This one is going to the enable pin. Okay, so we'll label this one. And the label is going to be register input enable. And then this one is the register input register selection. So we'll call this register input. Let's see, how did I label the other one? Register in. Okay, so this will be register in selection. What did I do?
You should have the labels face somewhere other than west. You have label location. Only thing, you have label location as west. You can put it as north
Or south.
Yeah. See right to your left.
Left.
Left. Move the mouse left.
No, it's facing
Label
north, which is right.
No. The label location is west.
Oh, okay, I see.
South.
I see.
There.
Thank you for the piece. Thank you.
Sorry.
This one I redo because I didn't save it. Register input selection. There we go. All right. So this is the input port of all the registers. So this is the register input data. Okay. So the input is all done. Now it's time to deal with the output. Basically the same deal. Okay. Because we have the enable and then we have the selection. So the enable can be tied together, okay? Because both of these will either be on or off at the same time. You can make them individual, okay, and let the design outside of the register bank to make the determination, okay? So, but basically it boils down to the same thing. We have, in this case, we have they're both input pins. Yep.
Is it less resources to use the multiplex? Is it better to use decoder than multiplexer? Why not feed just data through the multiplexer instead?
Okay, that's a good question. Okay, so the question is, why do we use a input data port and a decoder instead of a demultiplexer, right?
Yeah.
It has to do with the fact that each register has an enable already. So you can, so in the other design, okay, if you use a demultiplexer,
Yeah.
you still have to select which register should pay attention to get updated, right? So that means your demultiplexer is not doing, the demultiplexer cannot do that part. It cannot tell the registers which one should pay attention to the input port.
Okay.
So this way is actually simpler because each register already has its own enable pin or enable port. So all you have to do is to connect the input pin to everybody, and then use a decoder to say, okay, I only want you to pay attention.
Okay.
But the other way would work too. It's just that then you will still need a decoder to go to each individual register on top of, so your demultiplexer doesn't really do anything useful in that case.
Gotcha.
All right, so now we specify the outputs. So we have output pin facing south. Actually, we want the, let's see. Yep, facing north is right. We want a data bits, okay? And we put one for each multiplexer. This is the first output. This is the second output, okay? Hook up these two, okay, it's all good. And the rest is really to specify these 4 pins, okay? This is for selecting, and they have individual, okay? Each one has its own 3-bit selection pin as input. So we have input here, 3-bit. So I'll put 3-bit for this one, and 3-bit for the other one. And this is gonna look really ugly. I can see already. That's okay. It just looks ugly, but it will still work. And then we'll switch it back to 1 for the enable. Okay. We'll go to the, there we go. Switch to 1. Go. And then this one we'll have to kind of wrap around a little bit. That's why I said it looks ugly. I saw this coming. There we go. All right. Okay, now we have the entire register bank all done. Okay. All right. So this is really a big mess. So what we want to do is to look at the. Oh, by the way, this is a trick you can do too. If you use the main sheet to do something, and later on you want to turn it into another design, just change the circuit name. Okay, so now I can change the name of this guy to register bank. Okay, like so. And I forgot to label all of these, so we'll call this one, call this pin. Oops. We'll call this pin having the label location to the south. We'll call this pin register out 0. Selection, SEL. We'll call this one register out 1 selection. Okay, oops, and forgot to specify south. There we go. This would be register out 0 data. And this would be register out 1 data. And this is going to be the enable of the first one. So the name is going to be the same thing, register out 0 enable. And the last one is going to be the 1, register out 1 enable. There we go. It looks really kind of mumbled up because I did not have enough spacing and stuff like that. That's there we go. But we do have the design here. Okay, so we right click on this and say edit circuit appearance, which is going to be kind of ugly. Okay, so it's kind of hard to see what is going on here. You can move these pins around if you want to. Okay, so this is a good time to change the design so that it looks a little bit better. Okay, so in general, what you want is to put the input and output onto the same side. In this case, we certainly have some of these pins kind of going all over the place. These 3 are related to the inputs. Where's my reset pin? Okay, that's the clock. That's the reset pin. All right, so we have to kind of rearrange the pins a little bit because it really looks ugly at this point. So this is the clock line. So we'll take the clock line out. The clock line, you can put it anywhere you want because it's universal it applies to all the pins, and the reset line is the same way. So I'm gonna comment the clock and the reset pin right away so I don't lose track of that. So this is the clock and this is the reset. And this one, that's just the orientation marker. That's my data input. So the input is going to be on one side. I'll make it on the left-hand side. Now we have to look at all of the other pins and find out, okay, this is also for input. We'll put it on the left-hand side. This is also for input. We'll put it on the left-hand side. And this is for output. We'll put it onto the right-hand side. Right-hand side. Definitely right-hand side. Okay, so I have just moved the pins around, just to make the design a little bit better. So now I have to label each individual one. So which one is this one? If you kind of remember the original map, what it is highlighting, that's the data input port, right? Okay. So this is register input. So I'm going to write it down here. This is register input data port. Okay. And this one it connects to the decoder. And do you remember which part of the decoder this is connecting to?
The enable.
This is it's not the enable. Let me just double check. That's the selection. This is the enable. Okay, good. So we'll go ahead and comment it and say this is register input enable. And by the way, what is the purpose of the register input enable? What does it do?
It will prevent any of the registers from being activated or selected.
Yep, exactly. So if register input enable is a 0, or when it is not asserted, then none of the register in the register bank will pay attention at all to the register input data port.
And are those all those ports on the left connected to the CPU, or where
These are all inside the CPU. We are actually specifying a subcomponent inside the CPU. But it will interface with other things in the CPU. But right now, we're just kind of focusing on the register bank itself so that we can treat the whole thing as one single unit.
So if those are in the CPU, where is that information being originated from?
Well, that's a good question. Okay, the question is, let me just kind of repeat the question so it's recorded. The question is, I'm halfway through, labeling the ports, okay? But that's besides the point, because your question is, when we are done with this thing here, where are these pins or where are these ports connected to inside the processor. So data input for the register can come from the memory bus, because sometimes you want to load from memory into a register, but it will also connect to the ALU, because after a calculation, you might want to store the result of a calculation into a register of the register bank. Is that making any sense? Okay. But those two are not the only cases, because there are other components, inside the processor we haven't really touched on yet. Okay. But those are the two possibilities based on what we have talked about so far. And then this one is the selection, so we'll go ahead and label it. Register input selection. And its job is to specify which register should be the input register, because we can select one out of the 8 registers to store whatever data is presented on the data port. So now that we are done with all the input, let's take a look at the outputs. All right, this pin here. Okay, I have to move this one out so that I can focus on this guy. This is connecting to the selection of the first register output. So this is a register, so if I want to label it, it will be register output 0. This is the selection bit, okay? And by the way, this is kind of the old way of doing things. Okay, I'll show you one example of how you might want to do this, as a more object-oriented way and programming kind of way to say it. So let's pick out the next pin first. Okay, so let's pick out the next pin to document, which is this one here. I know most of you cannot really see where it is in the little picture. It's right here, okay, which is the enable of register out 0. Okay, so the way to write this, I'll only do it once here just to show you, just an example. This is register out bracket 0 dot enable. Okay, so that's kind of a more object-oriented way, that you are already familiar with. So if I look at the entire register bank as one single unit, it has 2 output ports. We're referring to the first one, so it has an index of 0. But of that particular thing, it has several components. Enable is one, the data port is one, and then the selection is the other one. So this is the kind of more object-oriented way of naming the components. I do not know in industry whether they do it this way or not. Okay, that one I do not know. But if you're familiar with programming, this makes more sense. Okay, it's more organized. Yep.
So you're saying it's like a little tiny array that's saying this is in this element is 0, 0, 0, 0. We don't want to enable it.
Well, yeah. So that the register bank is not driving that particular port. So if the register bank is not driving that port, whatever bus it connects to is now free to be driven by somebody else. Okay, so that's the whole idea, is to have the same bus going around with all the different components, and you use a single wire to basically say, okay, you shut up, you shut up, you shut up, you speak. But they will all be speaking on the same bus. The reason why you want to do that is because the data bus is wide. Okay, the data bus is 32-bit, 64-bit wide. But the enable pin is only 1. So it's easier to have a enable pin going in different directions, and basically just to control each component and say, you shut up, okay? But then you'll be shutting up all 32 wires, instead of using the other way of doing things, which is using the demultiplexers and the multiplexers, because they take in 32-bit wide input and they have 32-bit output as well. So you want to kind of use the enable ability of these components to control, to make sure there's no bus fight, instead of the other way, which is really much more complex and costly.
It's a RAM chip, right? We just want to select which one.
Right. So now we can place this component. Which way do you like better?
Good.
No, it's good.
Either one is okay? Okay. All right, so this one is definitely the output port, because it's a circle. So if I use the new way of doing things, this would be register bank output 0 dot data. So this would be the 8-bit wide bus, or 32-bit, depending on how wide a register is. so now I can do this. The question is, can I go back in and edit something that's already here? And it seems that way. Oh, this is out. One. There we go. Now we can put a big box around it. Get rid of this box. And then put a new box. Yep.
Is the output labeled correctly?
Oh, yep, you're right.
Switch the last.
Yep, I
one.
switched those two. Okay, make sure that's there we go. Thank you. So now we can put a big box around this whole thing. Oh, I better move something around a little bit. Move these two. Up. There we go. I have not found a way to snap the wires or snap the drawing, which would come in pretty handy. Okay. Oh, I didn't finish the design. There we go. All right. So now we are looking at the register bank as one single component in here. Are we still doing okay so far? Okay, so the next thing we do, well, we have 10 minutes, which is more than enough time to illustrate how to use the register bank as a whole. Okay, so what we'll do is to illustrate that part, and we'll go ahead and add a new circuit. This is going to be my new main circuit because I used the main circuit as my register bank already, so I can make a new one as the main one. So now I can click on register bank, just slap it here, and now we use it as one single component. Okay, which is great because now I'm hiding all of the complexity of the register bank behind the scenes and only have this many interfaces or these many ports exposed. Okay, but to do this, I still need to have all the pins to do it. So we'll still have to specify enough pins, to make this work. So this is a input pin, and we need input pins into just about every single one of these. So it will still take some time to get this to work. So we want it to face south. One for clock, one for reset, and then data register input enable needs one. Output selection, output enable, selection, enable. Should have fixed the directions all at the same time. So these I want to face east, these I want to face west. All right, we're getting there, As I said a little bit earlier, we have this already in the processor design. I'm just repeating the process, but as I'm doing it, I'm trying to explain, the various components. This one needs 8 bits because it's the actual data bit, so we have to change it to 8. This one is 3 because we have 3 bits to specify which register we're dealing with. On this side, we have 3 here and 3 here. So shift click will select multiple items, and you can edit multiple items at the same time if you select multiple items at the same time to begin with. So we have this. That. This goes here. This goes here. Go. And then we have the data pins, which are output pins. We want it to face west. And 8 data bits. Select one here. Control D. Select the other one here. There we go. All right. Now we have the entire design done. Now the question is, how do we make this work? Okay. In other words, how do we make use of the register bank? When you first power up, the reset line is going to be asserted. So in simulation mode, it's the same thing as holding this line asserted for a little bit of time and then releasing it. What this is going to do is to reset all the registers in the register bank to zeros. So everything starts with a particular known state when you power up your computer. Are there any questions about the role of the reset pin? Okay. So the next thing we want to do is, let's say we want to store a particular number into one of the registers. So when we number the registers, let's number the registers as A, B, C, D, E, F. Okay, so instead of using 0, 1, 2, 3, 4, 5, 6, 7, we'll just call those register A to register F. Which register do you want to store to?
C.
Register C, okay. So register C is which index?
2.
It's 2. So which port do we have to mess around with first to specify that's the register that we want to deal with?
Register in selection.
The register in selection, and we want to specify a 1 here to specify register C. Are we doing okay so far? What data do you want to store into it?
34.
Hmm? All ones? Okay, that's not really exciting. Just a lot of clicking. All right. Okay, so now we have everything done, okay? So the next we have to do is to select register in enable, because if I don't specify register in enable, I can change register in select all I want, but nobody's paying attention at all, okay? So if once I click register in enable, the decoder will now start to drive a single pin out of its output to assert one of the registers. Okay, it's saying, hey, you pay attention now. Okay, and the new content of the register is already presented in register in data. But at this point, the register is paying attention to all the pins, but it's not changing its content just yet. Why not?
You need to clock it.
Because we have to clock it. We have to go from a 0 to a 1 transition with a clock line. So it's already a 0, we clock it to a 1, we clock it back to 0. And now I claim that after this operation, most of the time you don't want to keep things enabled, so you want to disable the enable, because there's no need to keep it enabled, okay? All right, so at this point I claim that register C, the third, quote unquote, third register in the register bank should not have the content of all ones. Do we know that is the case? Not yet, okay? Because if all the components are now hidden inside that rectangle, we have no visibility at this point into the design itself. So what you can do is to click on the design itself, right click, and say view register bank. And it is I hope you can see it. It's FF, okay, where the cursor is. It is actually stored FF already. Sorry? And then the other part that you want to kind of at least pay attention to and notice is the input or the enable of every single register is a 0 at this point. And it has to do with the overall enable, which is this guy here, is a 0. So the decoder is driving all the lines to zeros and make sure that nobody is selected at this point. Are we doing okay so far with the steps of specifying the content to overwrite a single register? I can only overwrite one register at a time. Okay, that's because with any instruction that you might want to execute with this processor, you only want to store one result at a time. So I only need to specify one register as an input to overwrite. Are we doing okay so far with this? Okay. So what we'll do next is to specify two outputs. So I'll just go ahead and plant values in this case. So let's say I want register B as one of the output, and I'll say BB is the content, and then I want register A, B, C, D, E. I want register E to be the other output. Let's make this EE here. Okay. So I can actually doctor the content of the registers before I go back out into the main design and see what I need to do to specify I want register B to be output 0, and I want register E to be output 1 from the outside view of the register bank. Okay? Because that's how I specify values to go into the ALU to do all the calculations. So to do that, let's see, maybe just click that. Yep, okay. So now I have to perform the selection here. It's register B, so it is a 1. The other one is register E, which is 4. So we specify another 1 here. Okay. So these will basically just it's just setting up the demultiplexer so that the wires will be the tracks is switched correctly. Okay. But nothing is happening just yet because the enable is a 0. In other words, the demultiplexer is saying, well, I am paying attention to the input, but I'm not driving the output yet. The output is unspecified. When you see the output pins having X, that means it is not being driven. Okay, it's in the tri-state mode, which means it's just not getting driven. So now I can say enable. Okay. Do we see BB with the first one? I certainly don't see BB. I see zeros and ones. Well, let's do a base 2 binary to hexadecimal conversion. 1011 is 11 in base 10, and 11 in base 10 is B in hexadecimal. Okay, and we have 2 repeating patterns because we have 1011 and then we have 1011 again. So that's definitely BB. The other one is 1110, which is 14 in base 10. The 14 in base 10 as a single digit in hexadecimal is E. Because F is the last one, which is 15, so this is E, and we have 2 repeating patterns again, so this is definitely EE. So this is from the outside view, how you utilize the register bank. Okay. Now the question is, well, that's a lot of work. Okay, clicking all of these pins, the enables, the selections, the clock line and stuff like that. That's a lot of work. So who's going to do it?
We are.
You guys have the answer already. What homework assignment did you turn in? I hope you have turned in already. The music box. Okay, the music box is the one that will toggle these things. Here, sorting parts is not from the music box. This comes straight from individual instructions. Parts of an instruction will go here. Parts of the instruction will go here and here. But when we're talking about just the enable pin, those are all coming from the music box. So your music box is basically sequencing of all of the enabling. So it's controlling the train tracks, in a particular sequence, so that the whole thing will work as one single unit as a processor. Yeah.
Do you incorporate clock in the enabling pins, or how do you?
The clock line?
Yeah.
The clock is a universal perpetual type of clock, just like in the music box. It's on its own, it's just going to click, 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 click the whole time.
Well, how do
Okay.
you?
So what you need to do is to time the enable so that you only stay enable for one single rising edge duration of the clock. Okay? Because the same clock is going to the music box just like your homework assignment. So that's how you can basically specify, okay, we'll only clock the input for one clock cycle. And then we'll turn it off. We'll turn off enable. So the clock keeps going all day long, which is okay. But as long as enable is off, none of the registers is getting in is paying attention to the data line. Yep, go ahead.
But we've inputted 11111. What happens with that? Like it doesn't show.
Oh, that's because that's not the register that we are outputting right now. We are outputting register B and register E. Okay.
Okay.
So if you switch to register 010 that will begin that retrieves the content that we just specified.
So accessing the registry manually was the faster way to put in data.
Say again?
Accessing registry manually, like going in, typing in like EE or FF.
Well, yeah, because it's just a shortcut to do it, because I didn't feel like going through all the clock cycles to program the other two registers. So I showed you a way to kind of doctor the content of the registers, so I can show you how to get the output, or how to get the registers to the output. Now, there's one more thing that is kind of important. Occasionally, not all the time, occasionally you want the same register to go to both register output ports. Okay? Okay. There's no reason why you cannot add register A to register A to double the value of register A, right? So you can do the same thing here. You can basically specify the same register, and there's no problem, because the same register is now going to two different demultiplexers. It's just that both demultiplexers choose the same input, and now you have the same data presented into the two data ports of the output of the register bank.
And then will those two outputs like go to the ALU or something to add them together?
Most likely, because when you need both registers as output from the register bank, it is for calculation. Sometimes you want the output of the register bank to store into memory, but you can only store one thing at a time into memory. So that's why you only need one output from the register bank in those cases. So when you need both register banks, that's because you're doing some calculations, or something else that requires two registers. All right. Are there any questions about the design of the register bank itself, or how it fits into the bigger picture? Like how does it relate to the ALU? This is from the output of the ALU. These will feed into the input of the ALU. So now we have the way to do calculations. We can choose the result of what calculations, and then we also have a way to store the result of calculations into registers and use the registers to provide data for calculations. Okay? What is kind of not so clear right now is who is orchestrating all of these things. Who's saying violins, flutes, okay, percussion back there, okay? It's the music box. Okay? The music box is the conductor of the orchestra. These are the components of the orchestra. Okay? All right. So I'm going to stop the lecture at this point, and when we get to the lab, I will show you the solution of the homework assignment that was due this morning.